Good afternoon, all of you. In the previous sessions, we have learned what is diversity. In the last class, we have discussed what is diversity combining and what are the different techniques for diversity combining. The first type of diversity combining what we learned was called as selection diversity combining, which we have done in the previous class. So diversity combining means we have a receiver diversity, we have n number of receivers, we have too much, we have so many receivers, receiving antennas, each receiving the signal with different signal to noise ratio, and in selection combining we are selecting the signal or the path with which we have the highest signal to noise ratio. That was what we have seen. We have seen the outage probability and we have seen what is the probability distribution of the function, what we call it as gamma sigma, right? Yes or no? And two important things what we have seen. First thing is called as the outage probability. Outage probability means the probability that the received signal will not have minimum threshold value. The signal to noise ratio, the power will not be minimum so that it can be received and deciphered at the receiver's end. That is called as gamma naught, which is this gamma naught, which is the threshold value, right? Outage probability. Second one, we have found out the average probability of bit error or symbol error. These are the two things that we learned in selection combining. In today's class, we will be studying what is called as maximal ratio combining. I told you in selection combining we have selected the best, okay, the signal with the highest signal to noise ratio. In maximal ratio combining, we will be finding out we'll be considering all the signals, will be the output of the combiner, will be the weighted sum of all received signals. Suppose we have M branch diversity, we'll consider all the M branches with different weightages. So this is the same, the diversity, receiver diversity block diagram which we have seen in the previous class. So what happens in maximal ratio combining? The output is a weighted sum of all branches. So that we have this alpha I in all branches that are non-zero. While learning selection, we'll be comparing selection combining with maximal ratio combining very often because we need to understand the differences. That is one of the objectives of this lecture. The combiner output is gamma sigma and we will be analyzing. Last time we have made out this alpha I to be 0 in some cases, right? When there is only one signal that is being received. So the output of the combiner is gamma sigma. So in maximal ratio combining, the output SNR gamma sigma is given by R square by N naught. In other words, it is equal to sigma I is equal to 1 to M we have M branch, this is called as M branch diversity. So we are taking values from 1 to M, AI Ri square by N naught into sigma 1 to M AI square. So the objective in maximal ratio combining is to make AI in such a way that we get maximum the combiner output, that is gamma sigma. Okay, so our objective is to maximize gamma sigma so that we select an AI in such a way that we get the highest value for the combiner output SNR. Okay. As I told you that we have an proportion, we have different branches, M number of branches, and we are going to give weightage to each branch. Branch with higher SNR will have higher weightage. Okay. The branches with a high SNR should be weighted more than branches with a low SNR, so the weights AI square should be proportional to the respective signal to noise ratios, that is Ri square by N naught. So N naught is the PSD, as we have discussed earlier. N naught denotes the power spectral density PSD. So individual SNRs of I branch, say for example for the ith branch will be Ri square by N naught. So as we have discussed, our objective is to make AI so that we get to find out a value for AI so that we get the highest value of gamma sigma, that is the combiner output. For that we have two methods. The first method is called as is to take its partial derivative of this one, which we have done, or else the second method is Cauchy-Squash inequality. So on solving these by taking the partial derivative, we get the value of AI square to be equal to Ri square by M naught. So we get this AI square is equal to Ri square by N for gamma sigma to be maximum, right? So in that case, what will be gamma sigma will be I is equal to 1 to M Ri square by N naught, which is nothing but the gamma of I, the ith SNR value. From this what we learn, the average combiner SNR and the corresponding array gain increase linearly with the number of diversity branches M, in contrast to diminishing returns associated with the average combiner SNR in selection combining. There would be a very highly probable question about comparing maximal ratio combining with selection combining. So in most of these questions you need to answer all these points. As with the selection combining, the distribution of the combiner output signal to noise ratio does not remain exponential even there is a ray line fading on all branches. We are comparing selection combining with maximal ratio combining. Okay. So the distribution of combiner output is a chi-square distribution with m degrees of freedom, and the average value or the expected value is given by m into the average SNR, and the variance is given by 2m into average SNR. So in that case, we are going to define the probability distribution P gamma sigma of gamma, which will be equal to gamma m minus 1 e raised to minus gamma by average minus gamma, gamma tilde by gamma tilde raised to m minus 1 factorial, where we assume that signal to noise ratio is always greater than or equal to 0. For values below, for values that is not 0, that is even, we do not consider that. In all cases where gamma is greater than or equal to 0. So the distribution of the combiner output is given. Next important definition along with this is what is outage probability for a given threshold value of gamma naught. In maximal ratio combining, what is the outage probability? P out is nothing but P gamma sigma less than gamma naught. Which is equal to integral of 0 to gamma naught P gamma sigma of gamma d gamma. On substituting the value for P gamma sigma of gamma, which we have derived in the previous slide, we get the outage probability to be equal to 1 minus e raised to minus gamma naught by gamma by average SNR gamma tilde into summation of k is equal to 1 to m gamma naught by gamma tilde raised to k minus 1 by k minus 1 factorial. We are evaluating P of gamma sigma at gamma naught. Gamma naught is the minimum threshold frequency for which the, minimum threshold signal to noise ratio for which the outage does not happen. Okay, that's the threshold frequency. So we are graphically representing P out versus gamma by gamma naught. In that case, we are for maximal combining with IID, ray line, fading, independent and identical. So in that case, you can see that the SNR to average SNR keeps decreasing with the number of branches. You will be asked to write the significance of outage probability in different combining techniques. In that case, you need to explain all these with necessary graphs so that you get maximum marks. Then another Next definition, the average probability of symbol error. We have already seen that the average probability of symbol error is defined as integral 0 to infinity Ps of gamma, P gamma sigma of gamma d gamma. This is the definition in general for probability of symbol error. Now, the next slide or next few slides, we will be studying what is the average probability of symbol error in maximal ratio combining. We are substituting the value of probability of Ps of gamma. Okay, that is nothing but Q function of root 2 gamma. And after solving the integral and giving the value of capital gamma to be equal to root of the average SNR by 1 plus average SNR, we get this to be the average probability of bit error. That is nothing but 1 minus gamma by 2 raised to m, sigma m is equal to 0 to m minus 1 plus m or m into 1 plus gamma by 2 whole raised to m. We have to often compare with our selection combining technique. So when we compare with the graph what we have done in the previous class, when we compare it with the maximal ratio combining, we come to know that maximal ratio combining has much better performance than selection combining. As the number of diversity channel increases, it is highly proportional. So, a recap of what we have done so far. We have studied what is selection combining in the previous class. In selection combining, what we are doing is that we have an m branch diversity, we have m number of receivers. In that, we are selecting a receiver with the highest signal to noise ratio, which is given by Ri square plus n. Okay, so the disadvantage of selection combining is that we have to continuously keep monitoring which branch has the highest signal to noise ratio. In maximal ratio combining, we are giving weightages to all branches. Okay, we are not selecting the best, but we are giving importance to all, but in proportion with the signal to noise ratio. The branches which are having highest signal to noise ratio is given more importance. Is it clear? Or more weightage? That weightage is called as AI square. Okay, in that case we are finding out AI square by AI square, we got the value of AI square to be equal to Ri by n. Is that clear? With this we are coming to a conclusion of receiver diversity in diversity techniques. The next class we will be starting transmitter diversity. So receiver diversity means we have multiple number of copies being received at the receiver's end. In transmitter diversity, we have multiple transmitters, a number of transmission antenna. So receiver antenna, we call it as SIMO, single input multiple output, what we have studied in the first class of diversity. In transmitter diversity, it is called as MISO. MISO means multiple input, single output. This is how we are going to study. Okay, with this we come into a new technology called as MIMO, multiple input, multiple output, that we will be studying in the coming lessons. So thank you all for listening. Thank you very much.